Hi everybody. This time I will talk about uniform acceleration in relativity. And the reasons for that are twofold. Namely, it's fun and it's a response to Astronomy Simplified, number 1, Basics of Time and Distance by Moore. And in this excellent presentation, she ended with saying that you can use astronomy to disprove wild claims like the Earth is flat, for instance. And the way she did it was to say that if you have a flat Earth, and if you, as a flat earther, want this thing to have something that feels like gravity, you need to accelerate it uniformly. And you can't do that indefinitely because you will hit the speed of light, and that's not possible according to the Einstein's theory of relativity. And that's a problem because relativity is weird that way. You will not get to the speed of light using constant acceleration, and I will try to show why. However, this is not the main focus in this presentation. Instead, I will use a spaceship, and let this guy be an observer. But anyway, I'm not going to use general relativity here, even though the uniform acceleration is used as a starting point. I will only use special relativity, and the reason is it's possible to solve this problem in special relativity, and I assume that more people understand or can be led to understand a little bit about special relativity than general relativity. However, this is a kind of starting exercise in general relativity because you have something that behaves like gravitation. Also, I will try to use basic mathematics here, algebra, and a little bit calculus, and well, the transitions will depend on calculus, but reading the formulas should be possible without them, reading the results rather. And if you want a better introduction to relativity, or if you want to check out Moore's video, I put up links there. But now I will plow on and try to define what this is about, and so I will have to describe velocity and acceleration.
The first equation says that if you're looking at something moving at a constant velocity, you can measure said velocity by looking at the change in position over a fixed time interval. X stands for position, t stands for time, and delta means the change of, as in the change of position delta x and the change in time delta t. So if a car moves 100 meters in 5 seconds, its speed is 20 meters per second or 72 kilometers an hour. If the speed isn't constant, you will have to make the time interval so small that the velocity can be deemed as almost constant. So speed at a certain time is delta x divided by delta t when delta t goes to 0. This can also be called the rate of change of the position and is written as w equals to dx over dt, which in calculus is described as the time derivative of the position. Acceleration is the rate of change of the speed, or a equals to dw over dt, or d squared x over dt squared. Acceleration being the time derivative of velocity and velocity being the time derivative of position, we can call acceleration the double time derivative of position. If you have a constant acceleration, it's easy to go the other way too. So let's call this uniform acceleration g. The acceleration due to gravity at Earth's surface is 9.8 meters per second squared, or about 10 meters per second squared. We can go the opposite way and start from acceleration. Constant acceleration means that the velocity will change by an amount g each second. Thus, w equals to gt. So if an object falls 1 second, its speed will be 10 meters per second, and if it falls 2 seconds, its speed will be 20 meters per second. Galileo was the first to observe this. The mean velocity over a time t will be 1/2 gt, so the distance traveled will be 1/2 gt squared. So if an object falls 1 second, it will fall 5 meters, and if it falls 2 seconds, it will fall 20 meters. Thus you get a parabola-shaped path when you push something off a table or a cliff. So far, velocity has been described relative to a single inertial system. Galileo speculated that as long as there was no acceleration, all systems would experience the same laws of mechanics, so that you could get a universal mechanics. When Newton made his laws, those laws adhered to that principle. To describe two such systems, it's easier if they agree on the orientation of their coordinates and synchronize their clocks and positioning systems when they pass each other. This is the basis for the figure where the two systems have a relative velocity v. Thereafter, only the position of the axis of the relative velocity will differ, as the x-coordinate of the spaceship will move up relative to the x-coordinate of the observer. The result is that when you measure length as difference of position at a given time, this will be the same in each system. Also, time intervals will be the same. However, when calculating velocities in one system, you will measure change of position over a given time, and these rates of change will be different for different systems. So you get that velocity relative to the observer equals velocity relative to the other system plus relative velocity between the systems. This is why javelin athletes run before they throw the javelin. If they can run at, say, 7 meters relative to the ground and throw the javelin with a velocity of 15 meters per second relative to themselves, then the velocity of the javelin relative to the ground will be 22 meters per second, and the javelin will travel much further. Acceleration is the same transformed as untransformed though, since it is the rate of change of velocity and relative velocity between the systems do not change. So in Newtonian physics, uniform acceleration measured by a spaceship will be the same as the acceleration measured by an outside observer in another inertial system. Thus you could certainly move past the speed of light in Galilean/Newtonian physics, but how about in Einstein's relativity? The basis for Einstein's theories is that not only mechanics but all physical laws should be the same in all inertial systems, and in general relativity also all accelerated systems. This poses a problem though, because the laws for electromagnetism contains the speed of light. So if these laws are fulfilled in all inertial systems, then the speed of light, called c, must be constant for all such systems. So there actually is one absolute velocity. But that means that something in the Galilean transformations has to give. What has to give is the independence between space and time. A set of transformations that keep the speed of light constant, called the Lorentz transformations, is shown here. I'm not going to go through these in details, but note that if c is large in comparison to the other terms, then the transformations approaches the Galilean transformations. Also note the square root expression in the denominator, which will pop up later too.